Right now, at this very moment, something is happening 3.5 billion light-years away that should be impossible. Two of the most violent, most destructive objects in the known universe are locked in an embrace. They have been circling each other for longer than our solar system has existed, and every 12 years or so, with the precision of a Swiss clock, one of them slams directly into the other at a fraction of the speed of light. And then it happens again, and again, and again. What you just heard is not science fiction. It is not a hypothesis. It is one of the most thoroughly documented, mathematically predicted, and observationally confirmed phenomena in all of modern astrophysics. The object is called OJ-287, and it is about to completely reshape the way you understand space, time, gravity, and the nature of reality itself. Here is the shocking part. Astronomers have been watching this system since 1887, over 100 years of data, photographic plates, radio telescopes, optical observatories, space-based satellites, all of them trained on this one spot in the sky. And what that century of data revealed didn't just challenge our theories, it demolished them, and then rebuilt them into something far stranger and more wonderful than anyone had imagined. Stay with me, because by the end of this video, you will never look at the night sky the same way again. But before we go any further, if you are watching this and you have never subscribed to this channel, please do it right now. Hit that subscribe button and ring the notification bell. We go deep on topics like this every single week, and I promise you, what we are going to cover today is unlike anything you've seen on YouTube. And I want to ask you something right now in the comments. Tell me, what country are you watching from and what time is it where you are? I'm genuinely curious because OJ-287 is one of those subjects that people from physics labs in Tokyo to living rooms in Brazil are fascinated by. Let's see where in the world our community is right now. Drop your country and your local time below. I read every single one. Okay, to understand why OJ-287 is so extraordinary, we need to build a foundation. And I promise you, we are going to get to the mind-bending stuff very quickly, but you need these building blocks first, or the revelations won't hit the way they're supposed to. Let's start with a question. What is the most luminous, most energetic, most powerful object that can exist in the universe? The answer is something called a quasar. Think of it like this. You know how a lighthouse works. It sits on a rocky shore, and it spins a beam of light in a circle, a single, concentrated beam that is visible for dozens of miles across dark water. Now imagine that lighthouse, except instead of a bulb, it contains the energy output of an entire galaxy of 100 billion stars, all compressed into a region smaller than our solar system. And instead of spinning a beam every few seconds, it blasts radiation in all directions, 24 hours a day across billions of light-years of space. That is a quasar. The word itself stands for quasi-stellar radio source. They were first identified in the 1960s by astronomer Alan Sandage and radio astronomer Thomas Matthews, who noticed these objects in radio surveys of the sky that looked like faint stars, but were producing far more radio energy than any star could. In 1963, astronomer Martin Schmidt cracked the code. Quasars weren't nearby. They were the most distant objects ever observed, and their luminosity was so extreme that only one mechanism could explain it: a supermassive black hole at the center, consuming matter at a furious rate. Here's what will blow your mind. The supermassive black hole at the center of OJ-287, the primary, the big one, is estimated to contain the mass of approximately 18 billion suns. 18 billion suns, all compressed into a single point in space. To put that number in perspective, our entire Milky Way galaxy has a central black hole called Sagittarius AC, which contains about 4 million solar masses. OJ-287's primary black hole is roughly 4,500 times more massive than the black hole at the center of our own galaxy. It is one of the most massive black holes ever measured anywhere in the observable universe, and it has a companion, a smaller black hole, still containing approximately 150 million solar masses, orbiting around it in a dance that has been going on for millions of years. This is the system known as OJ-287, and the closer we look at it, the more impossible it seems. Coming up next, we are going to talk about how astronomers figured out that OJ-287 was a binary system at all. And the detective story behind that discovery is one of the most incredible in the history of science. But first, we need to talk about light, because light is the only tool we have for seeing a system 3.5 billion light-years away. And the way light has been lying to astronomers for a century, and how they caught it in that lie, is going to change everything you think you know about observational astronomy. Before we go any further, I want you to picture something. It's 1887. George Eastman has just invented roll film. The Eiffel Tower hasn't been built yet. Electricity is a luxury for the wealthy. And somewhere in a cold observatory, an astronomer is pointing a telescope at a faint, unremarkable smudge of light in the constellation Cancer. A smudge that has no name, no significance, and no apparent reason to be interesting. They take a photographic plate. They file it away. They have no idea that they have just captured the first ever image of one of the most dramatic gravitational systems in the known universe. This is how the OJ-287 story begins, not with a bang, but with an archive. Fast forward to the 1970s. A Finnish astronomer named Eimo Sillanpää is digging through historical records of variable sources, objects in the sky whose brightness changes over time. And he notices something strange about OJ-287, which by now has been catalogued as a BL Lacertae object, a type of active galactic nucleus known for rapid, unpredictable brightness variations. The brightness of OJ-287 is not just varying randomly, it is pulsing. And those pulses, those dramatic spikes in luminosity, appear to repeat on a cycle of approximately 11.65 years. Now here's the critical thing about that discovery. A single period of brightness variation could be a coincidence. 2 periods could be a fluke. But when Sillanpää and his colleagues, including Mauri Valtonen, a Finnish astrophysicist who would go on to become the world's leading expert on OJ-287, combed through over a century of archival photographic plates and found the same repeating pattern going all the way back to 1887. That is no longer a coincidence. Something was causing OJ-287 to brighten on a clock-like schedule. And the most logical explanation, the one that survived every mathematical test thrown at it, was a second black hole. Think of it like this. Imagine you are standing in a dark room and you notice a candle flickering every 11 seconds. At first, you might think it's just a draft, but then you realize, what if there's a fan rotating in the room, and every time the fan blade passes in front of the candle, it creates that flicker. The candle is OJ-287's primary black hole, blazing away, and the fan blade is the secondary black hole, orbiting around it, and twice per orbit plunging through the accretion disk, the enormous swirling disk of superheated gas surrounding the primary, and sending twin blasts of radiation outward with each crossing. That is the mechanism. 2 bright flares per orbit, separated by roughly a year, repeating every 1165 years. A cosmic metronome ticking away across 3.5 billion light-years of space. By the 1990s and early 2000s, Mauri Valtonen had assembled a team and built the most detailed mathematical model of OJ-287 that had ever been attempted. And this model, built on the framework of Einstein's general relativity, did something remarkable. It made predictions. Specific, testable, falsifiable predictions. The model calculated exactly when the next outburst flares would occur, down to specific dates, sometimes down to specific weeks. And then the astronomy community watched and waited. In 2007, the predicted flare arrived, right on schedule. In 2015, another flare, on schedule. In 2019, a flare was predicted for July 31st, with an uncertainty of plus or minus 4 hours. Not days, hours. Mauri Valtonen and his team published this prediction in advance, and a flotilla of telescopes, including the Spitzer Space Telescope, in what would be one of its final observations before being decommissioned, were pointed at OJ-287 on that date. The flare arrived within the predicted 4-hour window. Across 3.5 billion light-years of space, a system of 2 colliding black holes sent a flash of light to Earth that Einstein's equations, written in 1915, had predicted to within 4 hours. Let that sink in. A theory developed over 100 years ago, applied to a system we can never visit, never touch, never directly measure, produced a prediction accurate to 4 hours. That is not luck. That is one of the most precise confirmations of general relativity ever achieved. Why does this matter? I can hear some of you asking, okay, but why does this matter? So two black holes are dancing around each other. Why should I care? Here's why. Because OJ-287 is not just an interesting object, it is a laboratory. It is the most extreme natural laboratory in the observable universe for testing the laws of physics. Every prediction it confirms, every measurement it enables, every deviation from expectation it reveals, all of it is refining our understanding of gravity, space, time, and the fundamental structure of reality. And here's your cliffhanger before we go deeper. Some of those predictions are telling us something deeply unsettling, something that Einstein himself would never have expected, something that suggests our universe is even stranger, and the relationship between these two black holes even more violent than even the most optimistic physicist had hoped. That is what is coming. Keep watching. What if I told you that the most destructive force in the universe also creates some of the most elegant, most mathematically beautiful patterns that physics has ever described? Welcome to binary black holes. And buckle up, because this is where things get genuinely strange. Before we talk about what OJ-287 is doing right now, we need to understand how two supermassive black holes end up in orbit around each other in the first place. Because this is not obvious. In fact, it was one of the biggest unsolved problems in astrophysics for decades, a problem so thorny it was given its own name, the final parsec problem. Here's how it works in theory. Galaxies are not static. Over cosmic timescales, they move toward each other, pulled together by gravity. When two galaxies merge, and this happens constantly throughout the universe, the supermassive black holes at their respective centers begin to sink toward the center of the newly merged galaxy. This sinking process is called dynamical friction. The black holes interact gravitationally with the stars around them, losing energy and spiraling inward. Think of it like this. Imagine two bowling balls dropped into a tub of thick honey. Each ball creates a wake of disturbed honey around it, and those wakes slow the balls down, pulling them toward the center. Gravity does the same thing to black holes, using stars as the honey. The two black holes spiral in toward each other. They get closer and closer. But then something strange happens. Within a distance of about 1 parsec, roughly 3.26 light-years, the black holes run out of stars to interact with. They've ejected or consumed the stars in their immediate vicinity. And without those gravitational interactions, they should stall. They should get stuck, circling each other at the same distance forever. This is the final parsec problem. And for decades, theorists couldn't figure out how two supermassive black holes ever got close enough to merge. It was a genuine crisis in galaxy formation theory. But OJ-287 tells us that, at least in some cases, the problem does get solved. Something pushes these black holes past that final parsec barrier. Maybe it's gas dynamics. Maybe it's a triaxial galaxy shape that creates new orbital paths for stars. Maybe it's a third black hole perturbing the system. Maybe it's all three, we don't know for certain. But in OJ-287, two black holes have definitively crossed that threshold, and they are now separated by less than 1/10 of a light-year, extraordinarily close for two objects of this mass. Now let's talk about what this orbit actually looks like, because it is nothing like the neat circular orbits you picture when you think of planetary systems. The orbit of the secondary black hole around the primary is not circular. It is highly elliptical, stretched out into a long looping path. At its closest approach, the secondary comes within a fraction of a light-year of the primary. At its farthest, it swings out to several light-years away. The orbit traces a rosette pattern, not a simple ellipse, but a precessing ellipse, one that rotates around the primary over time. This precession is not a quirk or an imperfection. It is exactly what Einstein's general relativity predicts for an orbit in the curved spacetime surrounding an 18 billion solar mass black hole. The precession of the orbit is, in fact, one of the key measurements that allows scientists to confirm that the primary black hole has the mass they think it does. Here is the mind-blown moment. The precession of OJ-287's secondary orbit is approximately 39 degrees per orbital period. Compare that to Mercury, our fastest precessing planet, which precesses by just 43 arc-seconds per century, one of the most celebrated confirmations of general relativity in our solar system. OJ-287's orbit precesses by 39 degrees, not arc-seconds but degrees, every 12 years. It is general relativity on steroids, happening in real time across intergalactic distances. Twice per orbit, the secondary black hole plunges through the accretion disk of the primary, and plunges through is perhaps the most catastrophically understated phrase in astrophysics. The accretion disk of a quasar like OJ-287 is not like a ring of dust. It is a churning, blazing, magnetic inferno of gas and plasma, heated to temperatures of millions of degrees, extending for hundreds of billions of kilometers. The gas in the disk is moving at a significant fraction of the speed of light. The magnetic fields threading through it are billions of times stronger than anything that exists on Earth. When the secondary black hole, an object containing 150 million solar masses, plunges through this disk at high velocity, it punches a hole through it. It drags material behind it. It heats the gas so violently that two enormous bubbles of superheated plasma, called plasmoids, are formed on either side of the disk. These plasmoids are the size of our entire solar system. They expand and cool, and as they do, they radiate enormous amounts of thermal energy across a broad spectrum of light. This is the flare. This is what Earth's telescopes see. This is the clock that Valtonen and his colleagues have been reading, and that clock is telling us something about how Einstein's universe actually works. Something we are going to explore in the next section, in a way that I promise will make your brain hurt in the best possible way. Here's a question that I want you to sit with for a moment. How do you test a theory of gravity at the most extreme possible conditions? Conditions that exist nowhere on Earth, nowhere in our solar system, nowhere even in our galaxy. When the only tool you have is light that took 3.5 billion years to reach you. This is the challenge that OJ-287 was made for. Albert Einstein published his general theory of relativity in November 1915. It took him 10 years of the most intense mathematical work of his life. And what it described was not gravity as a force, the way Newton had described it, but gravity as geometry, as the curvature of spacetime itself. Think of it like this. Imagine a rubber sheet stretched flat. If you place a heavy bowling ball on it, the sheet curves downward around the ball. Now roll a marble across the sheet. The marble doesn't travel in a straight line. It curves around the bowling ball, following the contours of the warped rubber. That curved path is what we call gravity. Einstein said that's exactly what is happening with planets, stars, light, everything. They follow the curved geometry of space-time, and we experience that curvature as gravitational force. Now in OJ-287, we have two bowling balls, one weighing 18 billion solar masses, one weighing 150 million solar masses, and the sheet of space-time around them is not gently curved. It is violently, catastrophically warped. The geometry of space-time near these objects is so extreme that effects that are mere footnotes in our solar system become the dominant physics of the system. When physicists compute the effects of general relativity on an orbiting system, they expand Einstein's equations into a series of correction terms, what they call post-Newtonian corrections. The first correction accounts for the precession of orbits. The second correction adds effects from the energy carried away by gravitational waves. The third correction adds more subtle coupling between the orbital motion and the spins of the objects, and so on. In our solar system, you generally need only the first or second post-Newtonian correction to get accurate predictions. The higher order effects are real, but they are so small they are nearly impossible to measure. In OJ-287, the system is so massive and the orbit so close that Valtonen's team needed to go all the way to the fourth post-Newtonian correction, a level of mathematical precision that had almost never been tested observationally before. They needed to include effects like the spin-induced precession of the primary black hole, the quadrupole moment of the primary spinning mass, and the effects of the system losing energy to gravitational wave emission. And here is the breathtaking part. All of those corrections, all of those higher-order effects that had previously been theoretical curiosities with no way to measure them, OJ-287 confirmed them, every single one. The 2019 flare prediction, which was accurate to within 4 hours, required including all of these corrections. Without them, the prediction would have been off by months. The precision of the OJ-287 data is so high that it is now one of the strongest tests of general relativity ever conducted. Stronger in some specific ways than even the LIGO gravitational wave detections. There is a remarkable theorem in theoretical physics called the no-hair theorem. It was developed through the work of Werner Israel, Brandon Carter, and Stephen Hawking in the 1960s and 1970s, and it states something almost absurdly simple. A black hole once formed is completely characterized by just 3 numbers: its mass, its electric charge, which is almost always negligible, and its spin. That's it, 3 numbers. No matter what fell into the black hole, stars, gas, planets, information, none of it survives as distinguishable structure. The black hole has no hair. It is perfectly bald. All information about what created it is gone. This theorem is central to black hole physics, but it had never been tested in a dynamical, real-world binary system. Because to test it, you need to know the spin of a black hole, and measuring the spin of a distant black hole is extraordinarily difficult. OJ-287 changes this. The precession of the secondary's orbit is sensitive to the spin and quadrupole moment of the primary black hole. By measuring that precession with the precision that a century of observations allows, Valtonen's team has been able to constrain the spin of the primary to a specific value and verify that the system behaves exactly as the no-hair theorem predicts. OJ-287 is not just confirming general relativity, it is probing the deepest, most fundamental properties of black holes themselves. In the next section, we are going to talk about something that makes even this seem ordinary by comparison. Because OJ-287 doesn't just test our theories of gravity, it is producing gravitational waves, ripples in spacetime itself, on a scale that dwarfs anything LIGO has ever detected. And those waves are headed toward Earth right now. On September 14, 2015, at 5:51 in the morning Eastern Time, a ripple in spacetime, created by 2 black holes colliding 1.3 billion light-years away, passed through the Earth. It squeezed and stretched the planet by a distance about 1,000th the diameter of a proton. The LIGO detector caught it, and the world changed forever. Gravitational waves had gone from a theoretical prediction of general relativity to an observed, confirmed phenomenon. Kip Thorne, Rainer Weiss, and Barry Barish received the Nobel Prize in Physics in 2017 for this discovery. That detection was extraordinary, but the gravitational waves from OJ-287, if we could detect them, would make LIGO's signals look like whispers. Every time 2 massive objects orbit each other, they radiate gravitational waves. The more massive the objects and the closer they are, the more powerful those waves. LIGO detects waves from black holes with masses of tens of solar masses. OJ-287's primary contains 18 billion solar masses. The gravitational wave luminosity, the power being radiated in gravitational waves, from OJ-287 is truly staggering. Estimates suggest it is radiating gravitational energy at a rate of roughly 10 to the power of 43 watts. That is more than the combined electromagnetic luminosity of all the stars in the observable universe. Think of it like this. Imagine standing next to a single candle in a dark room. That candle is the total light output of a trillion suns. Now imagine something radiating 100 times more energy than that, but entirely in gravitational waves, completely invisible to our eyes, our cameras, our radio telescopes. That is OJ-287 pouring energy into the fabric of space-time with every orbit. Here is a fascinating question that sounds like it should have an obvious answer. If OJ-287 is producing gravitational waves of such extreme power, why hasn't LIGO detected them? The answer lies in frequency. LIGO is sensitive to gravitational waves, with frequencies between roughly 10 and 10,000 Hz, vibrations happening tens to thousands of times per second. These are produced by stellar mass black holes and neutron stars in their final spiraling moments before collision. OJ-287's secondary takes about 12 years to complete one orbit. That is a gravitational wave with a frequency of about 1 cycle per 12 years, far, far below what LIGO can detect. To detect gravitational waves from systems like OJ-287, you need a detector the size of millions of kilometers, which is exactly what is being built. The Laser Interferometer Space Antenna, LISA, is a joint project of the European Space Agency and NASA. It will consist of 3 spacecraft flying in a triangular formation, separated from each other by 2.5 million kilometers. It is scheduled for launch in the mid-2030s, and when it goes online, OJ-287 will be one of its primary targets. The gravitational waves from OJ-287 will be detectable by LISA, and they will allow us to probe the system with a completely different tool than light. For the first time, we will be able to listen to OJ-287 as well as watch it. But here is something that should make your jaw drop. We may already be detecting the faint gravitational wave background from systems like OJ-287, not with any single detector, but with an array of ultra-precise cosmic clocks called millisecond pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radio waves with extraordinary regularity, some of them ticking more precisely than atomic clocks on Earth. Astronomers have been monitoring arrays of these pulsars for decades, and in 2023, multiple independent collaborations, Nanograv in North America, the Parkes PTA in Australia, the European Pulsar Timing Array, and the Chinese CPTA, all announced evidence for a gravitational wave background signal in their pulsar data. A low-frequency hum permeating all of space, likely produced by the cosmic population of binary supermassive black hole systems throughout the universe. OJ-287 is a member of that population. It is one of the loudest voices in that cosmic symphony, and we are just beginning to hear it. We are going to pause for a moment now, because this is a good time to zoom out. We've been going deep on the physics of OJ-287, and you're doing great. Coming up, we are going to talk about something that will make all of this feel personal. We're going to talk about what this system tells us about the ultimate fate of our own galaxy. And then we are going to go somewhere even more bizarre, into the question of whether 2 colliding black holes can actually produce effects that change the nature of spacetime itself. Every orbit of OJ-287's secondary black hole around the primary ends slightly closer than where it started. Not by much. Not something you'd notice over a human lifetime, or even over the entire history of recorded science. But it is real, and it is relentless, and it is pointing toward an inevitable conclusion. OJ-287 is decaying. And what happens when that decay completes, when the secondary finally spirals in and merges with the primary, is one of the most violent, most energetic events the universe is capable of producing. How fast is the orbit shrinking? The mechanism that is draining energy from OJ-287's orbit is gravitational wave emission. Every orbit, the system radiates gravitational energy into space, and that energy has to come from somewhere. It comes from the orbital kinetic energy. The orbit gets smaller. The orbital period gets shorter. The secondary moves faster, and the gravitational wave emission increases, which shrinks the orbit faster, which increases the emission further. This is a runaway process. It started slowly, it will end catastrophically. Mari Valtonen and his colleagues have calculated, based on the current orbital parameters, that the 2 black holes in OJ-287 will merge in approximately 10,000 years. In cosmic terms, this is tomorrow morning. Within 10,000 years, a length of time shorter than recorded human history, 2 of the most massive black holes ever observed will combine into a single entity. In the final seconds before the merger, after millions of years of gradual orbital decay, the secondary will be completing thousands of orbits per second around the primary. The gravitational wave emission will spike to unimaginable levels. For a brief fraction of a second, the merging black holes will release more energy in gravitational waves than all the electromagnetic radiation produced by all the stars in the observable universe combined over that same instant. Think of it like this. Imagine a pair of figure skaters spinning in a complex orbit around each other. As they pull their arms in, they spin faster and faster, angular momentum conservation, Now imagine those skaters weigh 18 billion and 150 million times the mass of the Sun. And instead of slowing down due to air resistance, they're losing energy to ripples in the fabric of space-time itself. The faster they spin, the more energy they lose, the faster they spin, until they simply collide. The resulting single black hole will oscillate. It will ring like a bell, emitting a characteristic gravitational wave signal called a ring-down. From that ring-down signal, you can read off the mass and spin of the final merged black hole. This is called black hole spectroscopy, and it is one of the most powerful tools general relativity gives us. When OJ-287's two black holes finally merge, the resulting black hole will not have a mass equal to the sum of the two original masses. Some mass will be converted directly into gravitational wave energy and radiated away. Based on the mass ratio of OJ-287's pair, the energy radiated in the final merger could be equivalent to several % of the total mass, meaning that billions of solar masses of matter will be converted directly into gravitational waves in a fraction of a second. And here is a detail that almost no one talks about. The gravitational waves from the final merger of OJ-287 will produce what physicists call the gravitational wave memory effect. This is a permanent, lasting shift in the geometry of spacetime. Not a ripple that passes and leaves everything as before, but an actual lasting change in the distances between objects. Spacetime, after the wave passes, will literally be a different shape than it was before. Any sufficiently sensitive detector within a large fraction of the observable universe would register not just the wave, but a permanent offset in their measurements. The universe will literally be slightly reshaped. And here is the humbling perspective on that. The light from OJ-287 that we are observing today left that system 3.5 billion years ago. The merger, if it truly happens in 10,000 years as calculated, will send its signal to Earth in roughly 3.5 billion years. Our Sun will likely have already become a red giant by then. Earth may not even exist, but the gravitational waves will still be here, passing through whatever remains of our corner of the universe. That thought should both humble and electrify you. Before we continue to our next section, let me give you a quick pulse check. Are you still with me? Drop a OJ-287 is wild in the comments right now if your mind is thoroughly blown. I want to see how many of you are right there with me. And keep watching, because we are about to get into what this system is telling us about our own galactic future. And it is not entirely comfortable news. Okay, I want to shift gears for a moment, because everything we have been discussing, two supermassive black holes, orbital decay, mergers, gravitational waves, might feel abstract, like something happening in a distant galaxy that has nothing to do with your life, your world, your cosmic neighborhood. But here's what I want you to understand. OJ-287 is not just an interesting curiosity. It is a preview. It is a glimpse of a future that our own galaxy is already committed to experiencing. The Milky Way and the Andromeda Galaxy are on a collision course. This is not speculation. This is established science, confirmed through precise measurements of Andromeda's velocity using the Hubble Space Telescope, and later by the Gaia Space Observatory's proper motion measurements. Andromeda is currently about 2.5 million light-years away. It is approaching the Milky Way at roughly 110 kilometers per second, faster than any bullet ever fired on Earth, moving constantly, every second, every day since before our planet formed. In approximately 4.5 billion years, the two galaxies will begin to interpenetrate. They will pass through each other, swing apart, fall back together, merge. The process will take hundreds of millions of years. And at the center of each galaxy, at the center of the Milky Way and at the center of Andromeda, there is a supermassive black hole. The Milky Way's Sagittarius A contains roughly 4 million solar masses. Andromeda's central black hole M31 is estimated at around 100 million solar masses. As the galaxies merge, these two black holes will begin the long process of dynamical friction, sinking toward each other, and eventually forming a binary system, an OJ-287 analog. In our own backyard, 4.5 billion years from now. What will we experience? Now, I should be clear. The Milky Way-Andromeda merger will not be violent in the way you might picture. Despite two galaxies colliding, The individual stars are so far apart that stellar collisions will be rare. The night sky will gradually transform. Andromeda's spiral arms will grow and spread across the sky over millions of years, eventually merging into a new, larger elliptical galaxy. Our solar system will likely survive. It will be flung into a different orbit within the merged galaxy, but the Sun and Earth will almost certainly remain intact. The collision is not an apocalypse for individual stars. It is, however, a complete transformation of the cosmic neighborhood. And at the center of that new merged galaxy, the two black holes will begin their dance. The same dance we are watching in OJ 287 today, with the same physics, the same orbital dynamics, the same eventual fate. Two become one. Think of it like this. OJ 287 is showing us in real time what our galaxy is going to experience. It is a time machine, not one that sends us forward, but one that shows us our destination by letting us watch someone else who is already there. Here's what I want you to hold on to as we continue. You are not a passive observer of this story. The fact that you are watching this video, that you are curious enough to spend this time learning about something 3.5 billion light years away, that curiosity is the engine of everything we know. Every photographic plate taken in 1887, every observation from Imo Sillanpää, every mathematical model from Mauri Valtonen, every telescope pointed at that faint smudge in the constellation Cancer. All of it was driven by the same impulse you are feeling right now, the desire to understand, to look at the universe and ask, not just what is that, but what does it mean? You are part of a lineage of curious minds stretching back thousands of years, and the knowledge you are gaining right now about black holes, about gravity, about the ultimate fate of galaxies, is not separate from your life. It is the context for your life. The universe is not a backdrop to human experience. We are part of the universe understanding itself. Okay, deep breath. Because in the next section we are going to explore something that the OJ 287 data is hinting at, something that makes even the merger of two supermassive black holes look like a warm-up act. Here is a question that nobody thinks to ask, but that completely changes how you understand black holes. What happens to the rotation of a star when it collapses into a black hole? The answer is, it keeps rotating, all of it. Compressed into a point, but the angular momentum, the spin, is conserved. And a rotating black hole is a completely different beast from a non-rotating one. It is described by a completely different set of equations, discovered by New Zealand mathematician Roy Kerr in 1963, and it has a property so strange, so counterintuitive, that even physicists took decades to fully accept its implications. Around a rotating black hole, there is a region outside the event horizon called the ergosphere. In this region, space-time itself is dragged around with the rotating black hole, and nothing, not even light, can avoid being dragged along. This effect is called frame dragging, or the lens-thirring effect. Think of it like this. Imagine a bowling ball spinning in a vat of honey. The honey near the ball gets dragged around with it, spiraling along. The further from the ball you get, the less the honey is affected. Now replace the honey with space-time, and the bowling ball with an 18 billion solar mass black hole rotating at some fraction of the maximum possible spin rate. And you have the situation around OJ 287's primary. The primary black hole in OJ 287 is spinning, and its spin has a dramatic effect on everything around it. It twists the trajectories of infalling material. It twists the jets of plasma that erupt from the poles of the accretion disk, and, critically for the binary system, it influences the orbital plane of the secondary. How do you measure the spin of an object 3.5 billion light-years away? You cannot land a probe on it. You cannot even resolve it as anything other than a point of light. The answer is that you read the spin from its gravitational effects on the secondary's orbit. A spinning primary black hole causes the orbital plane of the secondary to precess, to wobble, like the axis of a spinning top. This is a direct consequence of the lens-thirring effect. The black hole's spin drags spacetime, which in turn tugs on the secondary's orbit. By comparing the observed precession of OJ 287's secondary orbit with the predictions of general relativity for different spin values, Valtonen's team has been able to constrain the spin parameter of the primary black hole. The best current estimates suggest that the primary is spinning at roughly 30 to 40% of the maximum possible spin rate, what physicists call a moderate Kerr parameter. This measurement has profound implications. It tells us something about how this particular supermassive black hole grew, whether it formed through orderly accretion of material aligned with its spin axis or through chaotic mergers that deposited angular momentum in random directions. A moderately spinning black hole like OJ-287's primary suggests a mixed history of both processes. It is a fossil record of billions of years of cosmic evolution encoded in a single number. And here's a retention hook that should keep you watching. The measurement of the primary's spin from the orbital dynamics of OJ-287 is more than just an interesting astrophysical fact. It is the best current constraint on a quantity that is deeply tied to what some theorists call the information paradox, one of the most controversial and unresolved problems in all of theoretical physics. We will get to that in a few sections. But first, there's something about the secondary black hole that nobody talks about, and it is just as extraordinary as anything we've covered so far. Quasars are not just glowing blobs of bright material. Some of the most powerful quasars in the universe, and OJ-287 is among them, launch relativistic jets, twin beams of superheated plasma fired from the poles of the accretion disk at velocities that are a significant fraction of the speed of light. These jets can extend for millions of light years, longer than the distance between our galaxy and Andromeda. They carry enormous kinetic energy. They heat the intergalactic medium. They can shut off star formation in entire clusters of galaxies. They are among the most powerful sustained phenomena in the cosmos, and in OJ-287, the jet is not stable. It wobbles, it precesses, it changes direction in response to the orbital dynamics of the binary system, like a garden hose being moved by an invisible hand. The exact mechanism of jet formation remains one of the open questions in astrophysics. The leading model, developed by Roger Blandford and Roman Znajek in 1977, proposes that the jet is powered by the rotational energy of the black hole itself, extracted via magnetic fields threading through the ergosphere. The spinning black hole acts like a dynamo, converting rotational energy into electromagnetic energy, which then accelerates plasma along the magnetic field lines into the jet. Think of it like this. Imagine a child's spinning top with strong rubber bands attached to the tip. As the top spins, it winds the rubber bands tighter and tighter, storing energy. When the rubber bands snap free, they fling something outward at high speed. The black hole's ergosphere is the spinning top. The magnetic field lines are the rubber bands. The jet is whatever gets flung outward at the end. This process, the Blandford-Znajek mechanism, requires a rapidly spinning black hole and a strong, well-organized magnetic field threading through the accretion disk. Both appear to be present in OJ-287. Here is something remarkable. Observations of OJ-287's jet with very long baseline interferometry, VLBI, a technique that links radio telescopes across the globe to achieve extraordinary angular resolution, show that the jet is not static. Its direction changes over time, and that change is correlated with the orbital period of the binary system. The secondary black hole, as it orbits and periodically disrupts the accretion disk, influences the magnetic field structure of the disk and consequently the direction of the jet. This is called jet precession, and in OJ-287, it is an additional observational tool for probing the orbital dynamics of the binary pair. You might think of it like this. The binary system is a clock and the jet is one of its hands. By watching how the jet moves, astronomers get an independent measurement of the orbital period and precession rate, another way of reading the same fundamental gravitational physics, but with a completely different observational technique. The consistency between the jet precession data, the optical light curve flares, and the mathematical model of the orbit is one of the things that makes astrophysicists so confident in their understanding of OJ-287. Multiple independent lines of evidence all converge on the same picture. That is how science works at its best, not with a single piece of evidence, but with a web of mutually reinforcing observations. Let me give you a sense of the scale here. The relativistic jet from OJ-287, at the largest scales we can observe, extends for tens of thousands of light years, many times the diameter of our entire galaxy. The plasma in that jet is moving at velocities exceeding 99% of the speed of light. The energy carried in that jet over its lifetime is sufficient to heat and disrupt the intergalactic gas for millions of light years around the host galaxy. This matters for galaxy evolution. One of the great puzzles of cosmology is why elliptical galaxies, the large red dead galaxies containing little star-forming gas, stopped forming stars. One leading answer is AGN feedback. The jets and radiation from active galactic nuclei like quasars heat and blow out the gas in the galaxy, cutting off the supply of material for new star formation. OJ-287's jet has been doing this to its host galaxy for as long as the system has been active. Black holes don't just consume, they shape, they regulate. They are the architects of galaxies, not merely their inhabitants. Next, we are going to step back from the physics and ask a bigger question. What does OJ-287 tell us about the early universe? About where supermassive black holes came from? Because the answer to that question is one of the most contested debates in all of modern astrophysics, and the stakes couldn't be higher. We are now halfway through our journey together, and I want to take a moment to remind you of something. You have just absorbed more rigorous astrophysics in the last hour than most people encounter in years. You understand binary black holes, general relativity, gravitational waves, spin dynamics, and jet physics at a level that would make most physics undergraduates envious. So give yourself credit for that. And now I want to add one more layer, one that may be the most destabilizing of all. The primary black hole in OJ-287 contains 18 billion solar masses. That is not just a large number, it is in some ways an impossible number. And the story of how a black hole that massive can exist and what that existence tells us about the history of the universe is one of the hottest debates in modern cosmology. The universe is approximately 13.8 billion years old. OJ-287 is 3.5 billion light years away, which means the light we are receiving from it left 3.5 billion years ago, meaning we are seeing OJ-287 as it was 3.5 billion years ago, when the universe was about 10.3 billion years old. So OJ-287's 18 billion solar mass black hole had already formed by 10 billion years after the Big Bang. That sounds like a long time. But here's the thing. Astronomers have found quasars powered by supermassive black holes at much earlier cosmic times. The most distant known quasars existed when the universe was less than 700 million years old. And some of these early quasars are already hosting black holes with masses of 1 billion solar masses or more. How does a black hole grow to 1 billion solar masses in less than 700 million years? The most efficient known accretion process, the Eddington limit, sets a maximum rate at which a black hole can consume material. Even at this maximum rate, growing 1 billion solar mass black hole from a stellar mass seed in 700 million years seems nearly impossible. There are several competing theories for how supermassive black holes seeded themselves in the early universe. The first is light seeds, the remnants of the first generation of massive stars, known as population 3 stars, collapsing into black holes of a few hundred solar masses, and then growing through accretion and mergers. The problem is that this process seems too slow to produce the billion solar mass monsters we observe at early cosmic times. The second model is heavy seeds, the direct collapse of enormous clouds of primordial gas, bypassing the stellar stage entirely and forming black holes of 100,000 to 1 million solar masses all at once. These would have an enormous head start on growth, but the conditions required for direct collapse are very specific and may have been rare in the early universe. The third and most speculative option is primordial black holes that formed in the very early universe, before any stars had appeared, created by density fluctuations in the primordial plasma. If such objects exist and were sufficiently massive, they could have seeded the first supermassive black holes, but their existence has not been confirmed. Visuals comparison chart of black hole growth timelines under different seeding models. OJ-287 is relevant to this debate in a subtle but important way. The fact that we can measure OJ-287's primary black hole mass to such high precision, 18 billion solar masses, and understand its spin and its orbital history, gives theorists a concrete endpoint against which to test growth models. If the growth history of this particular black hole can be reconstructed from its orbital properties, it constrains which seeding model is correct. This is ongoing research. The answer is not yet in. But OJ-287 is one of the critical data points. In the years since JWST launched in December 2021, it has been transforming our understanding of the early universe. Among its most striking findings have been high redshift galaxies that appear too massive, too evolved, and too structured to have formed as quickly as the standard model of cosmology suggests. Some of these galaxies already contain evidence for supermassive black holes. These findings may point to a need for revisions in our understanding of how the first structures formed after the Big Bang. And if our understanding of early structure formation changes, if we find that black holes seeded themselves more quickly, more efficiently, or through different mechanisms than we thought, then systems like OJ-287, sitting at the endpoint of billions of years of growth, provide a crucial anchor for any revised theory. The early universe is trying to tell us something about OJ-287, and OJ-287 is trying to tell us something about the early universe. The conversation is still ongoing, and the best chapters are yet to come. We are now going to step into territory that is genuinely unsettled. Not just challenging to understand, actually unsettled among the world's best physicists. The place where quantum mechanics and general relativity collide and produce something that doesn't quite make sense. The place where OJ-287, in a roundabout way, provides some of the most relevant data in existence. This is the black hole information paradox. In 1974, Stephen Hawking made one of the most surprising discoveries in theoretical physics. Black holes are not truly black. Due to quantum mechanical effects near the event horizon, they emit a faint radiation, now called Hawking radiation, with a spectrum that depends only on the black hole's temperature, which is inversely related to its mass. This was a stunning result. It meant that black holes slowly evaporate over enormous timescales, losing mass as they emit radiation. A stellar mass black hole would take far longer than the current age of the universe to evaporate. But eventually, any black hole will evaporate completely. And here is the paradox. When a black hole evaporates, what happens to the information about everything that fell into it? The laws of quantum mechanics, specifically the principle of unitarity, state that information cannot be destroyed. If you know the exact quantum state of a system at one moment, you can in principle reconstruct its entire history. Information is conserved. But Hawking's calculation showed that Hawking radiation is completely thermal. It carries no information about what fell into the black hole. If the black hole evaporates completely, emitting only featureless thermal radiation, then all the information about its contents has been destroyed. This violates the unitarity of quantum mechanics, Hawking versus quantum mechanics, two of the most successful frameworks in all of physics, directly contradicting each other. The information paradox has been raging in theoretical physics for 50 years. In 2019, a landmark paper by Ahmed Almhairi, Netta Engelhardt, Donald Marolf, Henry Maxfield, and Jeffrey Pennington proposed a potential resolution using concepts from quantum gravity and holography, suggesting that information does escape black holes, but through subtle correlations in the Hawking radiation that were not visible in Hawking's original calculation. The Page curve of black hole evaporation, named for physicist Don Page, was recovered using these new techniques, suggesting unitarity is preserved. But the solution raises new questions, and central among them is, what is the microscopic structure of a black hole? What are the quantum degrees of freedom that store the information inside? This is where OJ-287 becomes relevant. The precise measurement of the primary spin, mass, and quadrupole moment, and the confirmation of the no-hair theorem, constrains what kind of object a black hole can be at the macroscopic level. If information is ultimately stored in the quantum microstructure of the black hole, if the horizon itself has some form of quantum degrees of freedom, as some theories suggest, then that microstructure must be consistent with the macroscopic properties we observe. OJ-287 is not solving the information paradox, but it is setting the boundary conditions. It is telling us what any proposed solution must be consistent with. That is how progress works in physics. Not all at once, but one constraint at a time. I want to pause here and give you something to chew on. Everything we have discussed, the orbital dynamics, the gravitational waves, the no-hair theorem, the jet precession, is based on general relativity. And general relativity is, by every experimental measure we have, a spectacularly accurate theory. It has passed every test thrown at it, including the extreme tests of OJ-287, and yet we know, with equal certainty, that general relativity is not the final theory of gravity. It breaks down at the center of a black hole, at the moment of the Big Bang, at any point where quantum effects become important. It is incomplete. So we are using an incomplete theory to understand one of the most extreme gravitational environments in the universe. And it works. And we are using the results to constrain theories that might replace it. And those constraints will eventually help us build a better theory. This is the strange loop at the heart of modern physics. Using the theory we know is wrong to narrow down what the right theory must look like. OJ-287 is one of the most important tools we have for tightening that loop. Let me tell you about something called the OJ-287 monitoring campaign. It is one of the most sustained, most internationally coordinated observational efforts in the history of astronomy. Dozens of observatories on multiple continents, space-based telescopes, radio arrays, optical imagers, X-ray satellites, all of them coordinated in some cases around the clock to capture every nuance of OJ-287's behavior around predicted flare events. Why does monitoring OJ-287 require so many eyes? Because the flares are brief. They last days to weeks. They happen in multiple wavelengths simultaneously. And different wavelengths probe different physical processes. So to get the complete picture, you need to observe in radio, infrared, optical, ultraviolet, X-ray, and ideally gamma-ray wavelengths simultaneously. One of the most dramatic moments in OJ-287 science came in the summer of 2019, when the predicted flare was expected to arrive on approximately July 31st, within a 4-hour window. The problem was that OJ-287 was too close to the Sun at that time to be observed by ground-based optical telescopes. It was in solar conjunction. The Sun's glare blocked all attempts to observe it from Earth, but the Spitzer Space Telescope was in a different position in its orbit around the Sun. It could see OJ-287, and in what would be one of its last major scientific observations before being decommissioned in January 2020, Spitzer was used to observe OJ-287 during the critical window. The flare arrived on July 31, 2019, within the predicted window. The observation confirmed the mathematical model to an extraordinary degree of precision, and it did so using a telescope that was launched in 2003 and had been operating for 16 years, powered by a battery that was running low, observing a target 3.5 billion light-years away during a brief window of opportunity. Science doesn't always happen in the most glamorous circumstances. Sometimes it happens in a 4-hour window, on a dying space telescope, from a position in the solar system that no ground-based observatory could reach. You may have heard of the Event Horizon Telescope, the global network of radio observatories that in 2019 produced the first image of a black hole's shadow. The dark region at the center of M87 Kui, a giant elliptical galaxy 55 million light-years away. And in 2022, the EHT imaged Sagittarius A, the black hole at the center of our own Milky Way. OJ-287 is a target of interest for the EHT as well, though the imaging challenge is different. The primary black hole in OJ-287 is far more massive than M87T, 18 billion versus 6.5 billion solar masses, but it is also far more distant, 3.5 billion versus 55 million light-years. The angular size of the black hole shadow on the sky is comparable to M87 Cax, making it potentially resolvable with the EHT at full sensitivity. Imaging the shadow of OJ-287's primary, and perhaps seeing the influence of the secondary on the accretion disk, would be one of the most extraordinary scientific achievements of the coming decade. The coming decade will see a revolution in our ability to observe OJ-287 and systems like it. The Square Kilometre Array, SKA, will be the world's largest radio telescope, with collecting area more than 10 times any current radio array, enabling unprecedented sensitivity for monitoring the radio emission and jet structure of OJ-287. The Vera C. Rubin Observatory will scan the entire southern sky every 3 nights, catching unexpected outbursts. The Nancy Grace Roman Space Telescope will provide wide-field infrared coverage, and the 30-meter telescope and extremely large telescope will push optical and near-infrared sensitivity to new limits. All of these will be watching OJ-287. All of them will contribute to the most complete observational picture of a binary supermassive black hole system ever assembled. And what they will find, what surprises remain in this extraordinary system, nobody can predict. That uncertainty is not a weakness, it is an invitation. Science is not an abstract pursuit, it is a human one. And the story of OJ-287 is inseparable from the people who spent decades of their lives understanding it. I want to take a moment in this section to tell you about those people. Not just as names on papers, but as human beings driven by curiosity, delayed by funding shortfalls, energized by unexpected results, and ultimately rewarded with one of the most satisfying scientific confirmations of the 21st century. Aimo Sillanpää is a Finnish astronomer at the University of Turku, who in the mid-1980s began systematically analyzing the historical light curve of OJ-287. At the time, OJ-287 was known as a variable BL-Lacertae object, interesting but not particularly exceptional in a universe full of interesting objects. Sillanpää's crucial contribution was recognizing the periodicity. Working through photographic plate archives and early CCD photometric data, he identified the DAS 11.65-year periodicity and published the first paper proposing that OJ-287 was a binary supermassive black hole system in 1988. This was a brave hypothesis at the time. Binary supermassive black holes were largely theoretical, and the observational evidence for the periodicity was suggestive but not conclusive. The 1988 paper began the campaign of targeted monitoring that would eventually yield the extraordinary confirmation of the model 30 years later. If Sillanpää identified the phenomenon, Mauri Valtonen built the theory that explained it. Valtonen, a Finnish theoretical astrophysicist with a remarkable career spanning stellar dynamics, N-body simulations, and general relativity, became the central intellectual force behind the OJ-287 research program. Valtonen's mathematical model of OJ-287, refined over 2 decades with his collaborators, including Kari Nilsson, Hanna Kotilainen, and an international team of observers, is a tour de force of applied general relativity. It incorporates orbital mechanics, post-Newtonian corrections to multiple orders, disk-crossing physics, spin-orbit coupling, and gravitational wave emission. It has been refined with each new observation, and with each refinement, its predictive power has improved. The 2019 prediction, accurate to 4 hours, was the culmination of Valtonen's life's work on this system. In interviews, he has described the feeling of watching the Spitzer data come in and confirm the flare within the predicted window as one of the most satisfying moments of his scientific career. The OJ-287 story is also a story of international collaboration. Observers from Finland, India, the United States, Japan, Germany, Spain, Poland, and many other countries have contributed photometric, spectroscopic, and radio data to the monitoring campaigns. The coordination required to organize simultaneous multi-wavelength campaigns, accounting for different time zones, telescope schedules, weather conditions, and funding cycles, is a logistical challenge as significant as any scientific one. Stephanie Kamossa, a German astrophysicist at the Max Planck Institute for Radio Astronomy, has been a key contributor to the X-ray monitoring of OJ-287, providing crucial constraints on the accretion disk physics. Lankeswar Dey, an Indian astrophysicist working with Valtonen, has been central to the most recent model refinements and the 2019 prediction paper. Science is a team sport. OJ-287's extraordinary scientific legacy is the product of dozens of careers, hundreds of observing runs, thousands of data points, and one small, faint, blinking dot in the constellation Cancer that refused to be ordinary. I sometimes think about what it means to devote decades of a scientific career to a single object, to a smudge of light that no human will ever visit, that we understand only through mathematics and photons. What sustains that dedication? I think the answer is that OJ-287 is not really just one object, it is a window. Every measurement it provides opens a view onto something deeper, onto the nature of gravity, the behavior of spacetime, the history of the universe, the ultimate fate of matter. The object itself is almost beside the point. What matters is what it reveals about the universe we all live in. That is why OJ-287 matters, not because it is exotic, but because it is clarifying. We have arrived at the final leg of our journey together, and I want to use this last section to do something a little different. I want to pull together every thread we've woven over the past several hours and show you how they connect, not just to each other, but to you, to your life, to the way you see the cosmos. Because this is the thing about OJ-287 that I find most remarkable. It is not just a distant exotic object. It is a mirror, and what it reflects back to us is a picture of ourselves, of what we are, where we come from, and what we are capable of understanding. Let's retrace the path we've taken. We began with a shocking revelation. Two black holes circling and colliding for millions of years. Their crash is predictable to within 4 hours by a century-old theory of gravity. We then built a foundation. What quasars are, how binary black holes form, and why the periodicity of OJ-287 revealed its binary nature. We went deep into general relativity and saw how OJ-287 tests it at extremes that no laboratory on Earth can achieve. We explored gravitational waves, the cosmic symphony that OJ-287 is broadcasting across the universe, a symphony we are only just learning to hear. We watched the orbit decay, measured in real time, pointing toward a catastrophic merger 10,000 years from now. We made it personal by linking OJ-287's fate to our own galaxy's future. The Milky Way-Andromeda merger, billions of years hence, that will produce an OJ-287 analog in our own cosmic backyard. We explored the spin of the primary black hole, a fossil record of billions of years of cosmic evolution encoded in a single measurable number. We studied the jets, those extraordinary beams of plasma fired at near light speed across intergalactic space, reshaping the environments of entire galaxy clusters. We confronted the mystery of how 18 billion solar mass black holes even exist, a question that remains one of the deepest in modern cosmology, with JWST only deepening the mystery. We grappled with the information paradox, the unresolved conflict between quantum mechanics and general relativity that OJ-287 helps constrain. We surveyed the global army of telescopes watching OJ-287 right now, and the next generation of instruments that will see it with unprecedented clarity. And we met the scientists who gave decades of their lives to understanding a faint, blinking smudge in the sky. Every one of these threads is real. Every one of them is based on mathematics that has been checked, rechecked, observed, and confirmed. The universe is doing all of this, right now. Here is what I want you to take away from everything we have covered. OJ-287 tells us that the universe operates according to laws that are profoundly mathematical. The precise 4-hour accuracy of the 2019 flare prediction is not luck. It is the universe following mathematical rules with a fidelity that should astonish anyone who thinks about it carefully. Physics is not an approximation of reality. It is a description of reality, incomplete, always evolving, but increasingly precise. OJ-287 tells us that size and scale are almost impossible for human intuition to grasp. And yet mathematics spans those scales effortlessly. The same equations that describe the precession of Mercury's orbit around our Sun describe the precession of a 150 million solar mass black hole around an 18 billion solar mass colossus 3.5 billion light-years away. The universe does not care about scale. Physics is universal. OJ-287 tells us that the universe is old, violent, and beautiful. It has been running its grand experiment since the Big Bang, creating structures of breathtaking complexity, galaxies, stars, black holes, binary systems, through the application of a small number of physical laws. What appears chaotic on the surface is governed by deep order underneath. And OJ-287 tells us that we, creatures made of atoms, living on a small planet orbiting a middling star in a spiral arm of an ordinary galaxy, have somehow figured out how to read the universe's history, its present, and its future. That is extraordinary. That should fill you with awe. Here is the final mind-blown moment of this video, and I have been saving it. The light from OJ-287 that we observe today left that system when the universe was approximately 10.3 billion years old. When that light departed OJ-287, Earth did not yet exist. The Sun had not formed. The solar system would not coalesce for another 5 billion years. That light traveled for 3.5 billion years across an expanding universe, past galaxies, through voids, bending around gravitational lenses, crossing the entire intergalactic medium, and arrived at the Spitzer Space Telescope on July 31, 2019, at precisely the time that Mari Valtonen's equations predicted it would. And then human beings who evolved 3.5 billion years after that light departed, on a planet that didn't exist when the journey started, detected it, measured it, confirmed it, and used it to validate a theory developed by a patent clerk in Berlin in 1915. Think about the chain of coincidences that had to occur for that to happen. OJ-287 had to be in the right position in the sky to be discoverable in the 1880s. Astronomers had to save photographic plates that turned out to be scientifically priceless a century later. Imo Sillanpää had to look at a particular catalogue entry on a particular day and see a pattern. Mari Valtonen had to build a mathematical model precise enough to predict, years in advance, a 4-hour window. The Spitzer Space Telescope had to have remaining fuel to maneuver to the right orientation, and you had to be curious enough to watch this video. Every one of those links in the chain was necessary. Remove any one of them, and this particular story of human understanding does not happen. You are not separate from OJ-287's story. You are part of it. The story of OJ-287 is far from over. In fact, in many ways, it is just beginning. The LISA Space Observatory, scheduled for launch in the 2030s, will directly detect the gravitational waves from OJ-287's binary system for the first time. When it does, astronomers will have a completely independent measurement of the orbital parameters, a gravitational wave listened to complement the optical and radio look we have now. The consistency between the two will be the most powerful test of general relativity in a strong field binary system ever achieved. Pulsar timing arrays are already accumulating data on the nanohertz gravitational wave background, the aggregate signal from all the OJ-287 type systems in the universe. As the datasets grow and sensitivity improves, we may begin to resolve individual contributions to that background, OJ-287 prominent among them. The next predicted flare events in OJ-287 are being eagerly anticipated by the global monitoring community. With each new flare, the mathematical model will be further refined, the constraints on the system's parameters will tighten, and the window onto extreme gravity physics will open a little wider. And somewhere, in a photographic plate archive, in a radio data cube, in a space telescope's memory banks, there may already be information about OJ-287 that no one has fully analyzed yet. A new pattern, a new anomaly, a new question. The next Imo Sillanpää, the next Mari Valtonen, the next discovery. The universe is endlessly patient. It will keep doing what it does. Two black holes circling each other, crashing through each other's disk, sending light across 3.5 billion light-years, regardless of whether we are watching. But we are watching, and that makes all the difference. You have just spent over 3.5 hours, or whatever portion of this video you have watched, engaging with some of the most profound and complex science that exists. You have thought about black holes and space-time and gravitational waves and the fate of galaxies. You have grappled with questions that the best minds in physics are still working through. You did not need a physics degree to follow this journey. You needed curiosity. And you had it. That curiosity, the willingness to ask what is that, and why does it work that way, and what does it mean, is the most important scientific instrument ever built. Not LIGO, not the Spitzer Space Telescope, not the Event Horizon Telescope, not any of the extraordinary machines that humanity has constructed to probe the cosmos. The most important instrument is the human mind, aimed at the universe with the intention to understand. You have that instrument. Use it. The universe is extraordinary. OJ 287 is extraordinary. And so is every person who takes the time to understand them. If this video meant something to you, if you found yourself genuinely amazed, genuinely curious, genuinely changed by what you learned here, please share it. Not for my benefit. For the benefit of the person in your life who would be electrified by the knowledge that two black holes have been colliding on a 12-year schedule for millions of years, that a century-old theory predicted a flare to within 4 hours, that the universe is following mathematical rules of breathtaking precision, that we live in a cosmos that is violent and beautiful and comprehensible. Share it with the friend who loves science but lost touch with it after school. Share it with the student who is wondering whether physics is worth pursuing. Share it with anyone who ever looked up at the night sky and felt something they couldn't name. What they were feeling was the beginning of understanding. This video is one chapter of that understanding. Subscribe to this channel if you have not already. We do this kind of deep, serious, awe-inspiring science communication every week, and I promise you, there is no shortage of topics in this universe that deserve this level of attention. Until next time, keep looking up, keep asking why. And remember, the universe is not something happening out there, beyond you, separate from you. You are the universe, awake and wondering. Never stop wondering.